All right, nothing says like learning how to do a one-way between subjects ANOVA, like actually just jumping into the problem. So let's talk a little bit about what we have here. So in this case, what we're going to be looking at is Alzheimer's disease and trying to develop drugs that will improve cognitive ability, or at least maintain cognitive ability, if you want to think about it, in that way. And so what we've got is we've got two different research teams that have developed two different drugs that are going to be administered to a really homogeneous sample of individuals. Now, we don't talk about this much in our stats class, but today we're going to be really using a very homogeneous group. These will be men who are between the ages of 70 to 75 who've been diagnosed with Alzheimer's disease within the last 6 months. Now, again, that will remove a lot of potential alternative explanations and potential confounds that we may have to look at as far as our design is concerned, but we won't really be talking much about that, except for that it's a really homogeneous subsample that would be pretty traditionally used in a early stage project like this to see if it works on any sample, and then you look to see if it works on other subsamples. These 15 men will be randomly assigned into 3 different conditions, a placebo group, the first drug, which we'll just call drug 1, and the second drug, which we'll just call drug 2. After they've been on their drug, again, or the placebo, for 6 months, they will then be given the Montreal Cognitive Assessment Evaluation, which really taps into cognitive ability through memory, spatial reasoning, and executive functioning. All right, so what's the basic idea that we have here is that certain types of drugs, that's our factor, our independent variable, will explain variance in cognitive ability. That's kind of the easiest way to think about what we're doing. Now, the biggest difference between what we've done in the past and what we're doing today is that this is an independent subjects design. People are randomly assigned into one of 3 different groups. If we'd only had 2 groups, we would be doing this as an independent samples t-test. Today, we'll be doing this as a one-way between subjects analysis of variance. Now, I want to kind of do this sort of spoiler alert and show you sort of what the descriptive statistics look like. Now, in a typical design, we would actually go through the 4 steps, which means we would first state what our null and alternative hypothesis is. We would make our sampling distribution, or we would draw our sampling distribution. We would determine where our critical value is, and then we would analyze the data to ensure that we really understood what the data was telling us. However, just to try and understand what it means to partition variance, I want to sort of show you what this is right here. So here's what our results look like. Again, on the Montreal Cognitive Assessment, higher scores means better cognitive ability. And so descriptively, we can see some things that are pretty obvious, right? So descriptively, those in drug 1 are doing the best. They have the highest cognitive ability after 6 months. Again, now, you could say, well, that could have been due to a lot of things, but remember, we have a homogeneous subsample. We have people who are, excuse me, excuse me, we have people who are all men, individuals who have been diagnosed in the last 6 months, and they're all between the same age. And so that takes a lot of alternative explanations off the table. And what we can see is that these 5 men, have the highest average cognitive ability after 6 months, followed closely by drug 2, and last by the placebo group. Okay, so this may be what we would expect the population mean to be if there was no effectiveness of any treatment. And now we have to ask, are these 2 means different enough from both the placebo group and from each other to say anything about the population means, right? One thing that's really important is that we can see that the population means are different. And this is what we'll refer to as between subjects variance, right? That's the variance between the means, right? This is the between source of variance is another way to say it. And what it ultimately just means is, or the interpretation of the between source is that the means are not the same. So if I took these 3 means, which happen to be, I'll let you know this because we're using this data set, 21, 19, and 14, then we would be able to see that these 3 numbers, if we put them into an Excel file or an R file or SPSS or Jamovi, that those three numbers have variance. They're variable. The means are variable. Why might they be variable? Well, they might be variable because of sampling error, or they might be variable because of some sort of treatment effect. We did give some people different types of drugs. There's another source of variance that's really interesting here, which is if you look within each group, you can see that some scores are higher and some scores are lower, right? So why are the scores higher or lower in the placebo group? It's not because they're getting different drugs. They all got the exact same drugs. It's just that some people have naturally higher and naturally lower um, uh, cognitive ability scores even within the group, right? So we have these two different sources of variance. We have the within subjects variance and we have the between subjects variance. And what I like and what I want to really show is that we have these different types of variabilities that we can partition into different types of groups. And so I want to go to the whiteboard and sort of begin to describe this idea of a partitioning tree, which is similar to this graphic right here. And we'll begin to sort of see how we're going to understand the partitioning of sums of squares into their different sources. Okay, so the basic idea here is that we have these three different groups, right? We have these three different populations that we're interested in, right? So we have the placebo, we have drug 1, and we have drug 2, right? And then the dependent variable of interest here is cognitive ability, right? And so in the population, there would be, for our really restricted groups, 3 different population means. Now they could all be the same means or they could be different means. And there would be 3 different population standard deviations. Okay, so that's the kind of basic idea here. Now, what's important to remember is that this dependent variable is ultimately, if we took all 15 scores, we could get the variance for that, right? So we could get the variance for all of those scores, right? And how would we get the variance for all those scores? Well, we would take all 15 scores and we would take the sum of the squared deviations and we divide by the degrees of freedom. Now, we have how many people in this study? Even though they're broken up into 3 different groups, we have 15 total people in this design. So if we took all 15 scores and subtracted each score from the mean of all 15 scores, something we'll later call the grand mean, got the deviation scores, squared them, added them up, and divided by the degrees of freedom, we would get the variance within the entire study, right? That degrees of freedom is considered n minus 1. So I have, in this case, in what I will now call total to distinguish it in total. So this is in 1, in 2, and in 3, right? So I have 5 people in each of the groups, but I have 15 people in total. So I can say that the variance in total will be the sums of squares divided by 14. Now, what we do in ANOVA is something really interesting. We have this idea of total variance. Right, and total variance, which we saw on the previous slide, is really this value right here, right? It's the sum of the squares from all of the data divided by the total degrees of freedom. And what we're going to see is that what we do in an analysis of variance is we take the total sums of squares and the total degrees of freedom and we partition them into different sources, right? And this is sort of our explanatory model. And so the way that we think about, and one of the reasons I really like ANOVA is that it sort of takes us through this exercise. Why is the cognitive ability of these 15 men not all the exact same number? Right? Why isn't it a constant? Well, there's 2 really obvious explanations for that. So one is the between source. And this is the variance that's due to the treatment, right? So it's between treatment source. That is basically the one that says, hey, look, we did actually give people either a drug, two different types of drugs, or a placebo group. So maybe that has some reason for explaining why the variance is actually, um, maybe that explains a lot of the variance in these actual scores. Now, what's interesting here is that this is a variance component, right? All variance components have the same basic logic. They have a sum of squares in the numerator and a degrees of freedom in the denominator, right? So what that part of what we have to do is we have to actually find out, well, what is the between treatment variance, and what causes means to be different from each other. Now we'll go back to the slide and show that in just a second. We also see that within each of these groups, right, within the placebo group, there is variability, right? Some people have higher and lower scores. We might call that individual differences. We might call that sampling error. There's a lot of things that we can kind of throw into that. But the important part is that this is a within treatment, right? It's within the treatment. So the variability cannot be explained by getting a different drug because everyone in the placebo group got the placebo. So that cannot explain the variance. Everyone in drug one got drug one. That cannot explain the variance. Everyone in drug two condition got drug two. That cannot explain the variance of these scores, right? Now, again, this source has this variance takes on the same form, right? We have a sum of squares that we're going to need to compute for the within treatment or the within groups, if it's not an actual treatment, source, and a degrees of freedom that are associated with it. Now, what is super interesting to me is that the total sums of squares, whatever this number equals, will equal the sum of these two sums of squares, right? So in other words, when we're partitioning it, we're actually saying, well, some of the sums of squares total goes to the between source, and some of it goes to the within source. When we have degrees of freedom, we will partition and give, in many ways, or assign degrees of freedom into each of those. So if I have 14, which is the one number I know so far, 14 degrees of freedom, then the degrees of freedom between treatment and the degrees of freedom within treatment or within groups, if again, if we don't have a treatment variable here, has to sum to 14. So we're actually assigning or allocating those degrees of freedom to each of these two different groups. Now, as we sort of begin to move on, what we'll notice is that we have a few different goals here. One of them is to actually get the sums of squares and the degrees of freedom for each of the sources, and of course, make sure that everything sums up. But the last part is to actually take this variance and analyze it, right? Analyze all these variances. How do we analyze them? We're actually going to make a ratio of between or within subjects. Now I want to go back to the slide to explain why we do that. So on the whiteboard, we sort of saw this basic idea here, right? We have this between variability, that is the total variance on the t-dependent variable, basically when you ignore the group or treatment assignment, right? And then we take that and we partition it into, in this case, just two sources. One of the things that you'll notice in analysis of variance is that you just partition them into more and more sources, which is a really cool thing about analysis of variance is you always take the total variability and begin to assign them to different types of sources. So the between treatment variance and the within treatment variance both can be caused by one of the same things, which is random unsystematic factors, or sampling error is another way to think about it, but factors that's not attributed to the group. So, you know, as a personality psychologist, I often will say that, well, I mean, if you have people within groups, surely some people are going to be higher and lower just because of natural differences or individual differences. That is the thing that most explains it. So if people are different, and then you randomly sample out of populations, then populations will be different. The other thing that can clearly cause the between subjects to differ is that everyone was in a different condition or had a different treatment. This is a really cool part of analysis of variance. What it really shows is that these treatment effects are added to, or they're in addition to, these random unsystematic factors. So the way that we think about it is that these random unsystematic factors that are in both of these two different groups, right? Whatever causes people to be different at an individual level is what will cause means to be different at a group level, right? At least roughly to the same ratio. And that the only thing that can cause the means to be even further apart than random unsystematic factors are the systematic factors like a treatment effect, right? And in this case, it's the drug effect that's being added to that. So what happens is if we take the variance, the between treatment variance, and divide it by the within treatment variance, then if the only thing that is causing these means and these individuals to differ are these random unsystematic factors, then that ratio should be most of the time 1. Now, sometimes it'll be a little bit less than 1, sometimes it'll be a little bit more than 1 because of sampling error, but the modal event that we would expect if the null hypothesis is right is that the ratio between treatment variance over within treatment variance should be 1. What would cause it to be greater than 1? Well, I mean, of course, sampling error could cause it to be greater than 1, just random fluctuations. But if the treatment effect is the only other thing that can be added to the between treatment variance, then what we would see is a ratio that gets larger and larger and larger and larger and larger and larger. And what we see is the analysis of variance really takes this idea and says, we have this between group variability, which is the variability that's attributed to the means, which again is two things simultaneously. It is random unsystematic factors, which is also what's causing individuals to differ within their groups. But there's also a treatment effect, right? If the treatment effect is large enough, then the ratio should become more and more positive. What we will ultimately do as statisticians is we will draw a line in the sand for which we think the treatment effect is strong enough that we feel like, you know what, it's likely that that's what's really causing these differences. Or the other way to think about it is that it's unlikely that this is still just sampling error. And so basically the same sort of logic that we used with independent dependent samples t-test is still in play here. What could be causing these means to be different? Well, it could be that it's just sampling error. And if it's just sampling error, then we would see if you cross this out, I mean, sampling error is not this number 1 right here, right? So if the only thing that's driving the means apart is sampling error, then we have no systematic treatment effect. And then what we have is random unsystematic factors divided by random unsystematic factors. Now again, they're estimated through slightly different procedures, so you won't always get 1, but you should get 1 most of the time. Any event that leads you to something that's larger than 1 actually shows you that you probably are more and more likely to have a treatment effect. All right, so that's all the logic that we're going to be looking at this week. So let's sort of show how we're going to start doing this. Now, structurally, this will look very, very similar to all the stuff that we've done in the past. First, we have to express this research question as a statistical hypothesis, both as a null and as an alternative hypothesis. In this case, we will call that the original hypothesis in step 1 will be called the omnibus hypothesis. It will be the one that will try and encompass what the model will be showing explicitly at the 3-group level. You know, what can we say when we're comparing the 3 groups simultaneously? The reason that it's important to remember step 1 is because when we go to the sampling distribution, 1, we're going to learn a new distribution this week, and 2, if we don't keep track of that, then we might start to think that we're on different types of distributions, you know, or we might start to get different types of critical values or look things up differently. Now, the omnibus test is best tested through the creation of an analysis of variance summary table. If that analysis of variance summary table actually returns something that tells us that we should reject our null hypothesis, then as we'll see in step 3b, see I cheated a little bit there, right? Still 4 steps, just 3a and 3b with a lot of bullet points. All right, anyway, then we're going to do these post hoc tests. What's nice about the post hoc test is that the basic structure of these post hoc tests look nearly identical to the t-tests we've been doing in the past, so there will be some differences this week. Okay, so let's go back to our whiteboard and begin the process of talking about what is the null alternative hypothesis in step 1, which will be different, by the way, than any null alternative hypotheses in step 3b, right? So don't get ahead of yourself just yet. Okay, so the omnibus null hypothesis, the one that we're going to use to test the one-way analysis of variance, will start to look a little bit different than the type of hypothesis we've seen so far. Even though conceptually we've made statements that sound very similar to this, the way that we're actually going to write this null hypothesis is that population mean of 1, which is the placebo group. And again, you could always substitute in, especially if you're doing this by hand and you want to make sure that it feels really comfortable so that you understand it. You can put in, instead of 1, the placebo group is going to be equal to um, the population mean of group 2, which is also going to be equal to the population mean of group 3. Now, one of the things that's important here is that in an omnibus statement, right, I'm just saying that all population means are identical to each other. I cannot, in this situation, actually do the types of hypotheses we did with single sample tests because I don't know what any of the population means are. So I can't say they're all equal to a value. I can't say that population mean 1 equals population mean 2 equals population mean 3, which equals 4. Like I don't know what the population means are. So I don't have a comparison group. So I can't say what they're equal to. I also can't do the null hypothesis test that we did for an independent or dependent samples t-test. I can't say that, for example, population mean 1 minus population mean 2 minus population mean 3 is equal to 0, right? I can't say that those values are equal to 0, and I can't say that the differences, negative population mean 1 minus population mean 2 minus population mean 3 is equal to 0 either. Because if they were all some sort of number that's non-zero, then it would return a negative value, right? So don't write this, as a subtraction in any symbolic language, and don't try and write it as equal to something in any sort of symbolic language. And obviously, as I've tried to make a point about often, this is a statement about population means. Alternatively, and I write this a little bit different than some people, so I want you to sort of follow the logic here. If I reject this statement, I cannot say all the population means are different from each other because just one pairwise difference is enough to be able to reject this null hypothesis. So what I will say instead is that mean 1 does not equal mean 2 in the population. And then I have this language and or, right? That's one conclusion if I reject this omnibus test. Or it could be that population mean 1 is not equal to population mean 3. That could be true. And or population mean 2 is not equal to population mean 3. And what this really shows is that at least one but as many as 3 could be true, right? It could be that any one of these pairwise comparisons is true. And the reason I like to write it this way is it begins to set up step 3b under all circumstances, right? Because if I actually get to do step 3b, then what I'm really going to have to determine is how many of these alternative statements are actually true. It might be that only one of them is true. It could be that 2 of them is true. It could be that all 3 of them are true, right? That they're different from another population mean. But I don't know which one that is. All right, so now that's the first thing. And the second thing that I want you to notice is that if the null hypothesis is true, there is no way to test this through addition or subtraction, or even the assigning of a specific sort of value. So I'm going to have a completely new sampling distribution this week. I'm going to have an F distribution, which is used when I'm trying to look at the variability of group means, right? So I know one thing for sure. If these 3 numbers were all the same, if those 3 numbers were all the same, then the variance of those means would be 0, right? So if they were all 555, if they're all 666, if they're all 777, if they're all 888, whatever they are, right? If they were all the exact same number, then the variance would be 0. Now, even though that's true, the shape of this distribution doesn't look like the modal event is actually a variance of 0. Why is that? Because what's going to be on this distribution is an F ratio. The F ratio is going to be the between subjects treatment or the between source, if you want to think of it that way, divided by the within source, right? So I'm gonna get these two variances. So I could write them like this if you like. So there are two variances. I could take the between group variance and divide by the within group variance. Now, if you remember on the earlier slides, if these two variances are both being driven by sampling error, then the variance for the between source and the variance for the within source should be often approximately the same, right? So the null hypothesis actually assumes that the most frequent, if the null is true, right? So if the null is true, then the F ratio that I would expect most often is an F ratio of 1. Okay, so this is not rejection region over here, by the way, because this is an F ratio of 0, right? This is actually what explicitly the null hypothesis says. It just happens to be an infrequent event in variances because sampling error is very common, and so it'd be very, very uh, infrequent to get all three population means to be identical to each other. But if you did get an event over here on the left, this is in more support, not less, that the null hypothesis is actually true. So in this case, what that means is that to reject the null, the line in the sand that I have to draw is actually only going to be on the right side of the distribution, right? And remember, with a Z distribution, I had a Z critical value. With a T distribution, I had a T critical value. So guess what I'm going to have for an F distribution? Well, that's right, I'm going to have an F critical value. Now here's the thing that's interesting about the F critical value. The F critical value is actually going to need to get, it's going to be a ratio uh, of the two different sources of the degrees of freedom, right? So I need to know what the degrees of freedom are between the source and the degrees of freedom are within the source. Now I'm going to tell you what they are so we can look them up, and then we're going to explain why they're that way in a little bit. So this ends up being K minus 1. In this case, K is the number of groups. So I have 3 groups, 1, 2, 3, right? So K minus 1 ends up being 2 degrees of freedom will go on the denominator for the between treatment source. The within groups is N, total number of people, minus K, the number of groups, right? So remember a couple weeks ago I said that every time you have to estimate a standard deviation, and we won't formally do it through the descriptive statistics, but we will do it in the analysis of variance summary table. Every time we have to estimate a standard deviation, we lose a degree of freedom, right? And so we have 1, 2, 3 different standard deviations, so that we're going to lose 3 degrees of freedom. So we have the number of degrees of freedom total, the number of people total, which is 15, minus the number of conditions, which is 3, gives me 12 degrees of freedom. So I have 2 degrees of freedom in the denominator of the between treatment group, and I have 12 degrees of freedom in the within source here. So this will be an F critical value with 2 and 12 degrees of freedom, right? So I need to go look that up on a specific table. Now what's good here is that, remember, I partitioned the degrees of freedom, which I knew to be 14, right? That was this degrees of freedom from the variance component. So 14 got partitioned into 2 in the between source and 12 in the within source. And now I can go look up that critical value, and I have to introduce a new table in order to look up that specific critical value. So if you've used an F distribution before, this will look somewhat common. This is just a relatively easy one. It's not, that I have like some great infatuation with it, but it's a single page, and that's better than some of the other F distribution tables. It does note that there's D1 and D2. You should note that D1 is the degrees of freedom for the between source, and D2 is the degrees of freedom for the within source, right? So what that means is that I'm going to go over to column number 2, because this was the degrees of freedom I had for the between source, and I'm going to go down to right here, 12 degrees of freedom for the within source, right? The 2 and the 12 for the critical value. What does this mean? This means I need my F ratio to be 3.89 or larger in order for the treatment effect to be so large that it tells me that I don't think that this is just due to sampling error, right? That is normally the way that we think about this. So again, if this is a ratio of variances, then I need my ratio of between the variances of the means over the variances of the individuals within the groups to be almost 4. I mean, almost 4 times more variance between the means in order to say that I think there's likely a treatment effect here. Hey, but I can go back to my whiteboard and I can put that on the sampling distribution. And so I have 3.89 is my line in the sand, right? So what we've now set up, now that we've done the omnibus null hypothesis and the sampling distribution, is we've set up the next step. And the next step is going to be obviously to get the variance between groups and divide it by the variance within groups. That's going to give me my F ratio. I will then take that F ratio and put it on this sampling distribution. And if it exceeds 3.98, or if it lands right on it, then that's enough evidence to be able to reject this statement over here, and I'll go into the post hoc test. If it's anything less than that, right, this is all retain. All of this is retained, right? Everything over here is retain the omnibus null, and I'll basically skip step 3b. Spoiler alert, for this class, we'll always reject the omnibus null, so you can get used to doing that. Okay, that is enough information for you to now do the next 2 questions in this lecture.